Hi guys, welcome to our continuation of section 5.6 where we're finding inverses of functions. In class today, we found inverses of linear functions, if you remember, and what we did was to find the inverse of a function algebraically, we first switched the two variables x and y, and then we solved for y, and then we had the inverse function. And to graph the inverse, we could simply graph the original function and find some specific points on that line, and then just switch the x and y coordinates to graph the inverse. So that method of graphing the function in the inverse is much more easy to do when we're talking about functions that are not linear, which is what we're going to do now. So all linear functions are one-to-one, so every linear function has an inverse that is a function. The domains of many to one functions must be restricted in order to find an inverse. So if we look at example A, the reason we have that x is greater than or equal to 0 after the function is because this function is a quadratic. Remember that quadratics are many to one, so as they are given to us, they do not have inverses. But this one is f of x equals x squared minus 3 for x greater than or equal to 0. So let's first just think about the graph, x squared minus 3. If we think about it in terms of transformations, all we've done here is this minus 3 after our function, which means we have moved down 3. So before I graph that, I'm just going to remind us of the parent graph, and then we can shift it down 3, and then we'll restrict the domain. So remember that the parent graph of a parabola, f of x, equals x squared, has a vertex at 0, 0, and then every x value we just square, so it has the point 1, 1, 2, 4. That's the only one that's going to fit on our graph. I could do 3, 9, but that's not going to fit. If I go left, negative 1, 1, negative 2, 4. So this is the parent graph. So if we shift this down 3 units, my vertex is going to be at 0, negative 3. And from there, I can just count right 1 up 1, right 2 up 4, left 1 up 1, left 2 up 4. Okay, so that would be down 3. However, as that graph is in its original state, would not have an inverse because that's many to one. So what it tells us is to restrict the domain for x values greater than or equal to 0. So that means that the only part of the graph we are looking at is starting at the vertex here at 0, negative 3, and then the right side of the graph. Okay, oh, that's ugly. Okay, so it's like we have a half of a parabola. Okay, so what I'm going to do, just to make things simpler, I'm going to erase my original parabola and the left side of that. Okay, so this red graph right here is with our restricted domain. Okay, all right, so if I want to plot the inverse of that, I'm going to make a table of these values I have graphed for our original function. The first point is 0, negative 3. Then I have 1, negative 2, and 2, 1. Its inverse, just flipping the x and y coordinates, I will have negative 3, 0, negative 2, 1, and 1, 2. So negative 3, 0, negative 2, 1, and 1, 2. And then if I graph that, you can see that those two graphs are the reflections of each other over that dashed line y equals x. And that green graph is a square root function that we've been graphing before. So let's see when we do algebra what our actual inverse function is and see if it makes sense. Okay, so my first step in doing this is I'm going to write y equals x squared minus 3. Then I'm going to switch x and y. So x equals y squared minus 3. And I'm going to solve for y. So I'm first going to add 3. So I have x plus 3 equals y squared. Then to undo squared, we take the square root of both sides. And so I'm left with the square root of x plus 3 equals y. Now, because we put that square root in this function, when we write our inverse, we're also going to put the domain that goes with it. So f inverse of x equals the square root of x plus 3. And do you see that our graph starts at negative 3, 0 and goes to the right? So that's for x values greater than or equal to negative 3. That is our inverse function. And if we think of that in terms of transformations, if I had just given you that square root function and said, hey, what happened to the parent graph of f of x equals the positive square root of x, you would have said that it moved left 3. So that does make sense because our vertex, or our endpoint, used to be at 0, 0. Now it's at negative 3, 0. All right, let's do letter B. Okay. So letter B is f of x equals 2x squared for x greater than or equal to 0. So again, I have restricted my domain for x values 0 and greater. So that's just the right side of the parabola. And the only thing that's happened to this parabola is a vertical stretch by 2. Oops. So you can sketch the parent graph if it helps you. So 0, 0, 1, 1, 2, 4, negative 1, 1, negative 2, 4. So this is my parent graph. If I vertically stretch this by a factor of 2, my y-coordinates are going to be multiplied by 2. So 0, 0 will still stay here, but 1, 1 will change to 1, 2, and negative 1 will change to negative 1, 2. 2, 4 would change to 2, 8, so that would be somewhere up here, and negative 2, 4 would be negative 2, 8. So it'd be much taller graph and look thinner. Oh gosh. Okay, so however, we need this domain restricted. So we're only going to be taking the right side of our graph. So I'm just going to erase what I have there so I can make a neat graph with some points. Okay, so we have 0, 0, 1, 2, and just because I kind of want another point, I'm going to go ahead and kind of make some dots up here and say that this is 8. Okay, just so we can have another point on my graph. Okay. Great. Now remember, to find the inverse, I'm going to take those points and I'm going to reverse the ordered pairs. So I'm going to make a table of values. I had 0, 0, 1, 2, and then 2, 8. And so the inverse is going to be at 0, 0, 2, 1, 8, 2. So 0, 0, 2, 1. Let's see, this would be 5, 6, 7, 8, up 2. Okay, so there's the inverse. As you see, that looks like the square root function, but it's sitting at 0, 0 still, but it's been stretched now horizontally. So let's see what the function looks like when we do the inverse. So let's rewrite the function with y. So y equals 2x squared. Remember, we need to get rid of, well, first we need to switch x and y, So x equals 2y squared, but we want to get everything off of the y. So let's divide by 2. Now this is 1x over 2. I would prefer to write that as 1/2 x, and that equals y squared. To get rid of the squared, we take the square root. And so that leaves me with the square root of 1/2 x equals y. Writing that as an inverse function, I get f inverse of x equals the square root of 1/2 x. And I'm going to put the domain that I see that my green graph has. It has the same domain as the original. It's starting at 0, 0 and going to the right. That's for x values greater than or equal to 0. Let's think about transformations. Remember, when we have something multiplied by x on the inside, that's a horizontal stretch or compression. And we always do the reciprocal. So I have that 1/2 on the inside. I would flip that over and we'd say, hey, that's a horizontal stretch by 2. And sure enough, do you see that my points, we know our parent graph of our square root function would have had an endpoint at 0, 0, a point at 1, 1, but that point now is at 2, 1. So it's horizontally stretched by 2. And then we used to have a point at 4, 2, but now it's at 8, 2. Okay, awesome. So I just wanted to get through those quadratics so we get a little head start on our notes tomorrow. Tomorrow we're going to finish with these cubics. Okay, and then we're going to determine whether two given functions are inverses of one another, which is pretty simple. All right, guys, have a wonderful night. I will see you tomorrow.